are in the box, can we predict what reaction is going to occur? Would help if you can see what I can see. Because what tool do you need for that? Yeah, you need the table of those standard potentials. All right, so here's the relevant points. The bromine reaction. So the bromine reaction has a standard potential of positive 1.07 volts. The iodine reaction, reduction of iodide, is 0.54. Okay, from that information, predict the spontaneous reaction that would occur. You have fun with that. But not more fun than we're having. Okay, so what'd you get? What gets reduced? Bromine. Bromine has the more positive reduction potential. So bromine's going to get reduced. So bromine will be on the reactant side, and bromide will be a product. And then if bromine gets reduced, that means iodine has to get oxidized. So I've got to take the iodine reaction and flip it around. So iodide will be on the reactant side and iodine on the product side. There we go. That's it. Okay. All right, so that's just review. Questions about that?
Just if you had two different chemicals, and say, for example, the bottom one had 3 electrons, and so you have to do the thing where you multiply the top one by 3, bottom by 2. How does that change these numbers?
Okay, so yeah, if this, let's just pretend this is 3 here. So then add them together, you multiply that one by 2, and this one by 3. So all of the bromine things would now have a 2 in front of them, so this would be 4. And the iodines would be a 6, and that would be a 3.
Okay, so you multiply them all across.
Yes. But of course, it's not that way. Okay, so next what I'd like to do is take some of the powerful tools of thermodynamics that we talked about in our last chapter and apply thermodynamics to electrochemistry. You were hoping we could do that, I know. Now there's a relationship that we can come up with that actually makes quite a bit of sense, because for a spontaneous reaction, what do I know about delta G? It's going to be negative. What do I know about the standard potential for a spontaneous reaction? Positive. For a spontaneous reaction. Okay, so now let's think about if we can make an equation that relates these two to each other. So delta G equals something standard potential. So let's think about the units here. What units for gives energy? Joules, or joules per mole. But let's just use joules right now. And what are the units for potential?
Volts.
Volts, and a volt is a joule per coulomb. Okay, so in order to convert this to this, I gotta get rid of those coulombs somehow. And the other thing that I need to put in here somehow is the number of electrons that are involved in the reaction. Okay. but let's get to that later. The conversion factor that helps us with coulombs is Faraday's constant. 96,485, and the units are coulombs per mole of electrons. Remember, that's the conversion factor.
Are we gonna have to remember that number?
No. Don't, it doesn't hurt. I remember that. You want to be like me? But this is our conversion factor that tells us kind of the definition of a coulomb, right? How many moles of electrons it takes to get a coulomb, or really how many coulombs it takes to get a mole of electrons. So that, we're going to use that here. So I want to get rid of coulombs, and this has coulombs on the top. So what if I multiply E by F? So that gives me coulombs per mole of electrons. Now I've got coulombs canceled out, but I've got these moles of electrons here. So let's just multiply this by N, which is just the number of electrons, or the moles of electrons being transferred. Right? So that cancels moles of electrons, and cancels coulombs, so that I've got joules and joules. And then the last thing we need to do is to make sure that this thing is true, right? So if delta G is negative, potential should be positive. So there's the relationship between delta G and standard potential.
So those are delta G per mole?
Or just joules. It doesn't have to be per mole. Yeah, it's just joules. And the per mole is often implied. Okay. All right, so that's a pretty easy relationship to use, right? So, but looking at this equation right here, this reaction, can you figure out delta G? Go ahead and do that. You've got all the tools you need. The bromine reaction. Stand right here and then breathe. Oh yeah, so remember these right here are not real. But there's a problem over here. Yeah. Oh yeah, because those are both reduction potentials. So what do I put for N? 2. 2 moles of air. 2 moles of electrons.
Where did you get that? Is it just
Yeah, because bromine reduction uses 2 electrons, iodine oxidation produces 2 electrons, so it's that 2. So if I had, like the example I did earlier where I multiplied this by 3 and that one by 2, then it would be 6. Was that your question? Yeah, so it's just, however you write your equation, however many electrons are being transferred, that's the number you put in here. So that's negative 2 moles of electrons. Faraday is 96.45 coulombs per mole of electrons. And the standard potential is what? 0.53? That sounds right. Because this one, we make negative because it's going to go the other way. Yeah, 0.53. So that's what we put in here, 0.53. And then it's helpful to write the units as joules per coulombs so the units all work out. All right, so when you do that, 0.53 times 96.45 times 2, you
Joules
get
per coulomb, or volts.
negative 102,000 joules, or 102 kilojoules.
Why is it negative?
Because of the negative sign on it. That's so that a positive voltage, which tells us a spontaneous reaction, relates to a negative delta G. So notice that this voltage, which is kind of small, results in a very large